third lecture, we will keep on studying useful terms about op-amps. Even in this lecture, we'll study slew rate. Slew rate is the maximum rate of change of voltage versus time for the step input. Step input is this. If we apply this as input, step means that we take a step and jump to V in when we were at 0 volts. So this means a step. Step means a sudden jump. So if the input takes a sudden jump from 0 to a max value, maybe capital V, what is the way the output behaves? Can the output follow it exactly in the same way, or the output is a bit slow? Yes, the second thing is true. The output is slow. It cannot follow this sudden change of input as quickly as it was at the input. So it will take some time to rise to Vmax. This was Vmax. The input was risen to. So the input was raised to Vmax, but the output couldn't follow it exactly in the same way as the input rose, but output finally increased to Vmax by following this linear pattern. So this rise is executed in some time. We call it del t. So for this sample amplifier, we call it unitary gain non-inverting amplifier, when we'll study it further in the upcoming lectures. So it's a test circuit. For this test circuit and for all op-amp based circuits, the output cannot follow the step input as quickly as it was at the input. So it rises and goes to Vmax but takes some time, del t. So this change of voltage, del V, what is del V? This from here to here, this is del V. Delta V, this delta V out divided by del t is slew rate. So it's a very important parameter, and it shows a shortcoming of the amplifier, op-amp based amplifier, that quick changes at the input, but it takes some time for those changes to appear at the output, and the change of voltage divided by the time taken to observe that change at the output, the ratio of these two quantities, we call it slew rate. So it's a very important parameter. For example, if the input was raised from 9 volts to plus 9 volts suddenly, and voltage follow, it's a circuit that follows the same input, the same pattern. So even the output has to rise to plus 9 volts. But since the input was risen like this, it was raised to plus 9 volts as a step. So the output cannot do that. The output will go to plus 9 volt, but will take some time. So it's given that the time taken by the output to reach to plus 9 volts starting from minus 9 is 1 microseconds. So the net change del V is from minus 9 to plus 9. So this is an 18 volts change from minus 9 to plus 9 is a change of 18 volts. So 18 volts divided by 1 microsecond. So 18 volts per microsecond is the slew rate for this op-amp. Right. So it's a very important concept. Then the frequency response is the next thing that we are going to study. It's a wideband amplifier. All op-amps are wideband, and FCL is approximately 0 hertz. So they work from starting from slightly for frequency, slightly more than 0 hertz, slightly above DC, up to certain megahertz, and they don't require any coupling capacitors. Therefore, the lower cutoff frequency is very small. We studied earlier in this course that these coupling capacitor cause an FCL that is fairly larger compared to 0 hertz. Right, then we always use a negative feedback for these circuits. Negative feedback reduces gain. V out. Negative feedback is because if we have this as the input 1 millivolt applied to the non-inverting input and the inverting input is grounded, the output would be AOL times Vin. If AOL is 100,000, the output would be 100,000 multiplied by 1 millivolt is 100 volt. Of course, it cannot be 1 volt because it will be limited by, the output will be limited by the DC voltage we have applied for biasing. So the biasing voltage always limits these outputs. So it cannot be 100 volts, it will be limited. It will be limited at the biasing voltage. So Vout cannot exceed V supply. I have also mentioned it here. It cannot apply the DC biasing or the supply voltage. So what we have to do is, in the same way, if we apply a negative voltage, the output would be negative 100 volts, but cannot be. It cannot be negative 100. It will be limited at minus V supply. So to avoid these clippings, we use the negative feedback. That gives us a closed loop gain ACL. CL stands for closed loop, OL stands for open loop. ACL is much smaller than AOL. In other words, it is now controlled, and it gives us other advantages like increased input impedance, decreased output impedance, etc. So using op-amps in a closed loop with negative feedback is very advantageous. We'll study some sample circuits in the next lecture with feedback. Thank you.